Okay, let's look at integration by substitution a little bit. And when we showed that the integration by parts worked when we were talking about integration, we showed that the derivative, the product rule, gave us some derivatives, and we take the antiderivatives. That's what the integration was via the fundamental theorem of calculus. We're going to do the same sort of thing with the chain rule now, and substitution is the sort of inverse of the chain rule. So recall that the chain rule says if f and g are differentiable, I'm not going to say where the domains have to be, but in the right places, then f composed with g, or f of g of x, is also differentiable. And the derivative of f of g of x is equal to f prime of g of x times g prime of x. Right, so if I want to integrate or take the antiderivative of both sides, I get the integral of f prime of g of x times g prime at x dx is equal to f of g of x. And that's our chain rule, or our integration by substitution. And we always get to add in a constant, but this is an antiderivative for this stuff. Okay, so let's see some examples of how this works and talk a little bit about some techniques and things. So let's one of the hardest things to do is trig substitutions. So let's start with a trig substitution. So let's try and integrate 2x plus 1 over let's say x squared plus 4x plus how about 13. Okay, so why is this a trig substitution? Well, I can't use integrations by parts on it because the denominator is not factorable. There's no real roots with the denominator. I could factor it over the complexes, and I could use integration over the complex numbers, but we never defined that, and though it works out, you get complex solutions that turn real when you plug in real numbers, but that's not something that we want to deal with. So let's do a trig substitution. And so I'm going to factor this denominator a little bit. I'm going to complete the square, not actually factor it. And we're going to get 2x plus 1 over x plus 2 squared plus 3 squared. If I complete the square on the denominator, we get that, and we see that these two things are equal. Okay, that's almost good enough. Let's do one more trick. So if I could sort of split this up, the numerator, into a part where I could use the substitution directly, that'd be great, and then deal with the other part later. So let's try and rewrite this as these two things sort of together give me the integral of, well, if I wanted to use the chain rule on the top, I'd want a 2x plus 4. I've only got a 2x plus 1, so let's do 2x plus 4 over x squared plus 4x plus 13 dx minus the integral of 3 over x plus 2 squared plus 3 squared dx. And then now we can use substitution immediately on this piece. Let's say the inside function g of x is equal to x squared plus 4x plus 13. Then g prime of x is equal to 2x plus 4 dx. Okay. And then we can use our substitution there, and the left-hand integral, and we'll say the right-hand integral is, this is the integral of g prime of x over g of x dx, which is the natural log of g of x plus a constant. So that's going to be the natural log of x squared plus 4x plus 13. Okay, now we have to work with the right hand side. And so I've got minus this integral 3 over x plus 2 squared plus 3 squared dx. And now we get to do our trig substitution. So the first part was just a regular substitution, and the second part is going to be a trig substitution here. So by a trig substitution, I've got a sum of squares that sort of reminds me of a Pythagorean theorem. So we're going to draw a right triangle and be able to use the Pythagorean theorem with that sum of squares. This works with differences of squares too. But I don't see a substitution I could do to make this simpler algebraically, so we're going to draw a triangle and see if we can do a trigonometric substitution, which means that the variable is going to be an angle, theta. Let's call this theta, this angle right here. And to get this to match up with the triangle, well, I've got the sum of two squares would be the square of the hypotenuse. So let's make this the square root of x plus 2 squared plus 3 squared. And that makes one of these sides a constant and one of these sides a x plus 2. So let's make this side 3 and this side x plus 2. It doesn't really matter which side you put where, as long as you've got the hypotenuse as the biggest one. Most books have a preference, but the math works out sort of no matter which way you put the sides of the triangle here. Okay, so what do I have here? I've got 3 divided by the hypotenuse squared. So if I look at this, I've got that the opposite over the hypotenuse, or the sine of theta, is equal to 3 over the square root of x plus 2 squared plus 3 squared, which means that the sine squared of theta is equal to 9 over x plus 2 squared plus 3 squared. That's almost what I have in the equation here, but it's 3 times too big. So let's just divide by 3 on both sides. Sine squared of theta over 3 is equal to 3 over x plus 2 squared plus 3 squared. Okay, this is an equation relating theta and x. All of these things are equations relating theta and x. I could use any of these things as proper substitutions because they're relating the same variables in the same way. Okay, so this first one, I've got minus the integral of sine squared theta over 3 dx. And I could try and integrate this, but I've got a dx and I've got a variable of theta, which doesn't match up. So I need to integrate with respect to theta if I'm going to use this stuff inside. So I need to change this to a d theta. And we could use this equation here and get a relationship between d theta and dx, but there's a nicer equation to use, and I can use any of the equations that relate x and theta properly. So let's look at this equation here, which is x plus 2 over 3 is equal to the cotangent of theta. right? That's an easier function to differentiate. In fact, I get just 1/3 dx is equal to the negative cosecant squared of theta, right? Okay, so if I want to use that d theta, I can use this instead, and I can figure out that, well, dx right there matches kind of perfectly with this. So I've got the negative of the integral of the sine squared theta over 3 times dx is negative 3 times the cosecant squared of theta d theta. Okay, that's just replacing dx with its solution here. If I solve for dx, I get negative 3 cosecant squared theta d theta, right? So I'm just replacing dx with all of this stuff, and now I get a bunch of cancellation going on. This is actually just the integral of d theta, which is theta. Okay, that's nice, but how do I get theta by itself from this triangle? Well, I'm going to use this equation still. This is sort of the simplest one we have, and we'll just take the cotangent inverse of both of them. So we'll take cotangent inverse, the inverse cotangent function, not the tangent, not 1 over cotangent, but the inverse function of the cotangent, x plus 2 over 3 equals theta. So this is now equal to the cotangent inverse of x plus 2 over 3, and then another constant. So together I get the integral of 2x plus 1 over x squared plus 4x plus 13 dx is equal to the natural log of x squared plus 4x plus 13 plus the arc cotangent, or the cotangent inverse, however you want to say it, or however your book does it, like this, and then a constant. Okay. Most texts are going to be calling, well, the arc cotangent and the tangent actually just differ by a constant. So the arc tangent is what usually shows up in these things, but they just differ by pi over 2, I believe. And so we get this. Okay, let's try another trig substitution. Let's try the integral of 1 over x squared plus 1 cubed dx and see what happens with this. Okay, so I don't necessarily see right away that this is going to be a trig substitution, but I kind of do because I've got a sum of squares. The sum of squares gives me that I'm probably going to use a trig substitution, because this sum of squares, I can't use any other substitution for it. So we're going to draw the triangle that has that as its hypotenuse, right? And we'll take any angle inside here that we want that's not the right angle for our trig substitution, and let's go with x and 1 this time. I think I put the x on the bottom last time. Yeah, let's put the x on the side. So it doesn't really matter where the variable goes and where the constant goes, but let's do it this way this time. Okay, so what do I have here? This is equal to the integral of 1 over x squared plus 1 cubed. That's the adjacent over the hypotenuse cubed. That's the cosine cubed of x, of theta, and I've still got a dx. So I have to deal with that somehow. How do we deal with it? Well, x over 1 is equal to the tangent of theta. That gives me that dx is equal to the secant squared theta d theta. Now I can just replace that x dx with the secant squared theta d theta, and we end up with the integral of the cosine cubed of theta times the secant squared of theta d theta, and that's equal to the integral of the not sine, cosine cubed and secant squared cancel, so I get just the cosine of theta d theta, which is the negative sine of theta, and a constant. How do I calculate what this is? Well, I've got a triangle with an angle of theta in it already. The sine is the opposite over the hypotenuse, so this is negative x over x squared plus 1 and a constant. Okay. So that's kind of how trig subs work. And how regular substitutions work. Let me say one more thing. When you're doing these substitutions, you get relationships between two variables that you're trying to switch between, right? I'm trying to switch from an x to a theta, right? So I need some relationships between x and theta so that I can switch between them using those equations. Any equation that you get over here relating those variables is a valid use for a substitution. Okay. I can use this tangent equation, or I could have used the cosine equation. I could use the secant equation. I can use any equation I want. And this is true even if you just have algebraic stuff. It doesn't have to be trig stuff where you get different equations. So, like for example, maybe you get this substitution. You want u equal to be 2x squared plus 1. Okay, maybe that's what your substitution is going to be. You can use this equation directly, or you could use like u over 2 minus 1 and a square root is equal to x. You could use that. You could use that u plus 1 is equal to 2 times x squared plus 1. You could use that. That's a valid equation that you get from this. Add 1 to both sides and factor out the 2. So you could use any of these types of things. If maybe you see an x plus 1, but you also have a 2x plus 1 in your expression over here. Maybe it's something like maybe you have x plus 1 over 2x squared plus 1 dx, and you want to do a substitution like this. So you think u should be this, okay, maybe, and you can turn this into an integral of well, you get the u in the denominator, and you've got u plus 1 over 2 in the numerator. You'd still have a dx. Okay, so you could do any of these types of things, and you could get, well, 1/2 integral of u plus 1 over u dx, but then you'd have to figure out what to do with dx. You can take the derivative here or the derivative here. It doesn't really matter how you get the pieces of this. These guys are all equal as long as you use equations that relate the variables that come from the substitution that you want. In the triangle ones, the substitution we wanted was this picture substitution, basically. And that's substitution.